Okay, today I'm having a little trouble with the computer, so I'm going to have to somehow wing it without my slides. So that'll be interesting. All right, there we go. I got one set. Okay. There's still another one I wanted to copy over that I'm having some trouble with. That I don't think I'm going to be able to do. All right, so it'll be a little bit of a mixed lecture today. On our last lecture, we were working on a problem where we were going to solve using the power law generalized Newtonian fluid. So let's take a look at what we did so far. And this is actually part of the homework, so you're getting some slack here. Yep. Every now and then the stars come together and things work out, right? So let's see what we did. So we're solving this problem of pressure-driven flow in a tube at steady state, well-developed flow of a long tube. And we're trying to calculate the velocity field. So this is very different from predicting a material function. So we go back to the methodology that we used for Newtonian fluids, and we adapt it to the non-Newtonian fluids. So we started off with the continuity equation. So these slides indicate what you guys told me to do last time. And we started off by just comparing between a Newtonian and a non-Newtonian fluid. And we see that they both require they both contain the gamma dot tensor, del V plus del V transpose. So they both will insert themselves into the momentum balance in a similar way. So we started with the continuity equation. It's the same for the Newtonian and non-Newtonian. The only time it's different is compressible versus incompressible. And we said that the velocity field in the r theta z coordinate system was 0, 0, vz. So just writing that out at the beginning is helpful and lets us see quite a lot of what we know about the problem. So we eliminated Vr, v theta, and we got that dvz dz was 0. So that's everything that we were able to learn from the continuity equation. Then we move on to the momentum balance. So here's the momentum balance in vector tensor form in Gibbs notation. And the momentum balance, we can eliminate several terms right from the top. Steady state flow, unidirectional flow. If we're uncertain about this unidirectional flow, you can also get the tables and eliminate Vr, v theta, and dvz dz. The pressure gradient vector is easy. The gravity vector is easy, and then we spend some time on del dot tau. Now, del dot tau we can get from the tables. So we looked that up. And it's a big, enormous mess in principle, but it simplifies quite a bit for this simple unidirectional flow. So we took out theta derivatives and the fact that the stress tensor is symmetric. But these other cancellations we weren't able to do until we actually examined the constitutive equation. So starting with this equation, we realized we needed then to turn to the constitutive equation. And the constitutive equation for power law fluid is the generalized Newtonian fluid with the power law expression up front. So we had to get del V from the tables. So we cancel all the terms that are Vr and v theta and dvz dz. And we end up with a single non-zero term. So that single non-zero term, when we then say del V plus del V transpose, gives us this symmetric gamma dot tensor. Gamma dot will always be symmetric because a tensor added to its transpose will always give you a symmetric tensor at the end of the day. And our constitutive equations are always, right now, are proportional to gamma dot. And so they'll always give symmetric stress tensors. And then it became a little bit trickier, because here at this point, we now want to finish putting the constitutive equation together, and we need this m gamma dot to the n minus 1. And gamma dot is the magnitude of the gamma dot tensor. So now that we have the gamma dot tensor, we can take its magnitude by pulling out the definition of tensor magnitude from our notes, doing this across the diagonal product, and we get that gamma dot, the magnitude is just the absolute value of dv dr. But then in order to take the absolute value signs away or to choose the sign of the square root, we have to examine what is the sign of dv dr. So we sketch it in the coordinate system we're interested in, and we say as r increases, what happens to vz? And it decreases. So the slopes here are all negative. So because this is negative always, we can just choose minus dv(zr) in order to get a positive gamma dot. So that's the tricky part. Right? Now that we have gamma dot, the tensor, we can assemble tau, and we have gamma dot the magnitude. And so here's our constitutive equation, m gamma dot to the n minus 1 times gamma dot tensor. Here's the gamma dot tensor. Here's m. Here's our newly calculated gamma dot raised to the n minus 1. The minus sign raised to a fractional power is not a problem because this is negative also. So together they're positive. The fact that this is negative overall is okay. That's the correct sign of the stress. So then we multiply out, and only these two terms are non-zero. So we multiplied those out carefully, and we got m minus dv dr to the n is equal to tau. So putting that together, we got tau m gamma dot to the n minus 1 in those two positions. And we went back and reassembled the momentum balance. So here's the left-hand side, which was steady state unidirectional flow. That was 0. dp, the gradient of pressure vector, and then the del dot tau vector is the one that we need to evaluate, and there's gravity. Now we evaluated the del dot tau vector one term at a time, okay, by just going back to this matrix of del dot tau and picking up only the things that were not 0, which are one term here, no terms in the theta component, and one term in the z. So we evaluated those two terms. Here's the r component, putting in what we now know tau is. Because it's not a function of z, the whole thing goes to 0. The z component does not go to 0. It has these r derivatives in it, so we just plug in our tau component, and we have this term. So our momentum balance has dp dr equals 0, dp d theta equals 0, and this equation for the z component. So there's dp dr equals 0, dp d theta. And the z component is big, but not too difficult. If we bring these two terms to the left, it's a function of z only. This is only a function of r. Two functions of independent variables can only be equal if they're equal to the same constant. And then we were finishing up. And since it's a homework problem, I think I won't finish it up entirely, since I know you're dying to do that all yourself. Okay? So I just did the integration the last time. And you do have to apply the boundary condition early to proceed further from here. This becomes a little bit difficult to integrate. Yes, C1 is in fact 0 if you apply the boundary condition. So from here on, it's just calculus, which I'll leave to you. So at the end of the day, as I showed you at the end of class, this is the solution. It's in the class notes for the velocity profile in quasi flow, pressure-driven flow for a power law fluid. If we ask what is the stress, we have to go back to our expression for the stress tensor. But now we know the velocity field. So we can go back and pick up this derivative, raise it to the n power, multiply by m, and we'll get the stress. So we know everything about this flow. We know the stress at every point in this flow. If we want to calculate the average velocity, we have to integrate the velocity across the cross-section. Okay, so we have the velocity field. We could calculate the flow rate. The flow rate is the integral of the velocity across the cross-section. So the cross-section of the flow here, r d theta. R goes from 0 to r, theta goes from 0 to 2 pi. And then the average velocity is the flow rate divided by the cross-sectional area. So I plotted this solution here as a function of the velocity as a function of the average velocity. And when n is 1, it's a Newtonian fluid. So here's our Poiseuille flow, Hagen-Poiseuille law, pressure-driven flow in a tube for a Newtonian fluid. As we allow the material to be a non-Newtonian fluid, the velocity profile flattens in the center and scoots out a little bit toward the edges. Okay? And so the reduction of this power law coefficient as it gets smaller, the flow velocity profile gets flatter and wider. If you make it continuously get smaller and flatter and wider, it eventually becomes completely plug flow. Everything is just at the average velocity at all values, and it's just shoving straight through the tube.
So there's no methodology of obtaining those power law indexes, like on paper. It's got to be experimental work.
For a given material,
Yeah.
you have to measure it. You have to measure it. So you can either measure velocity profiles and compare them to these. That would be a very difficult way to do it. Or you can measure pressure drop flow rate in, if you measure the pressure drop flow rate, you can use the result for this expression, which I don't have in my notes, to back out what the power law parameter is by matching your pressure drop flow rate relationship. And that's essentially what we did last semester in the rheology class, in the rheology laboratory. Interesting, if you plot this result not as V over V average, but V over V max, it looks quite a bit different. And in some sense, it gives a good sense of the curve, because here's our Newtonian case, and then the non-Newtonian cases are flatter and flatter, but it doesn't conserve flow rate. These are over the maximum velocity. So I prefer this plot, which shows that the flow that you lose from the center, you gain on the sides. And that's how the velocity profile changes overall. Okay, so let's take a look at this second problem. Let's do drag flow, I think, because this one is actually fairly simple. Let's do drag flow of a power law fluid and see if we can carry this one out following the methodology that we just learned. Okay, so again, I am going to rely on you to start me off. How would I calculate the velocity field for the flow that's created when you put a power law generalized Newtonian fluid between two parallel plates and move the top plate at a constant velocity? This will be also a steady flow of an incompressible fluid. The plates will be very wide and very long. Now this one is in Cartesian coordinates, so we don't even need any tables for this one. Carl, how would you start this one off?
Start with continuity.
Okay, what's that?
That del V equals 0.
Yeah, del dot V equals 0. So that one we can do with our Einstein notation, d by dxi ei vp ep, if you haven't already memorized it. This is delta IP, and it's dv, I becomes p, dvp dxp equals 0. So this one is dv1 dx1 plus, dv2 dx2 plus, dv3 dx3 equals 0. So Warren, how does that simplify?
For this flow, it looks like dv1 dx1 is going to be 0, and so is dv3 dx3 because v1 is only a function of x2.
Yeah, v1 is only a function of x2. That's actually written here, but we can actually conclude it from this equation because v2 and v3 are 0. So that becomes dv1 dx1 equals 0 becomes the conclusion. But actually, your way of thinking is very common in fluid mechanics as well. If you examine each term and you see that you can logically say that they're all 0, then you end up concluding that you learned nothing new from the continuity equation. So that's a perfectly valid way to think about it as well. So we either learned nothing, or we learned that the velocity is not a function of the x2 direction. What's next?
Momentum balance.
Right. So the momentum balance is next. And I don't require you to memorize this, but this is it. dv dt plus v dot del v equals minus grad p minus del dot tau plus rho g. So Brian, what do you think? How does this simplify?
Well, the del P will only have one direction.
Unidirectional flow. What else?
You can say that rho G would be 0, negative G, 0.
Right? 0, negative g, 0. Anything else?
dv over dt is 0.
Because,
Steady state.
right. Anything else? Probably not, right? So this one we usually keep until we're forced to do anything about it, and this one is usually where the meat of the problem is, and that's also the case here. So you've done them all. So now we can write pressure, again from Einstein notation, d by dxi ei p, and so that's equal to dp dxi ei, which is dp dx1, dp dx2, dp dx3. And del dot tau we can also do from Einstein notation. d by dxj ej dot tau mp em ep delta jm, j becomes m, d by dxm tau mp ep. So we have a vector that is the sum of 3 terms in the x component, sum of 3 terms in the y, and sum of 3 terms in the z. And so it's d tau dx plus d tau dx plus d tau dx in each row. Now, Juan, can you tell me what are the subscripts? How do I fill in the subscripts here?
The x's will go 1, 2, 3 in the rows,
Right?
and then the taus will stay the same number for each row.
The first index stays the same number.
The first doesn't.
And the second index?
The changes 1, 2, 3.
Yeah, so the second index is 1's here, it's 2's here, and it's 3's here. So these are 1, 1, 2, 2, 3, 3. That's the m's going from 1 to 3. 1, 1, 2, 2, 3, 3. And then this P goes with which row we're in, which component of the vector we're in. And so this is the 1 component, and so this second index matches all 1s. And when P is 2, it's the 2 component, and this second index matches the 2s. And when P is 3, the index matches the 3s. So we've done that before, but maybe it's not as fresh because we haven't been doing that problem. All right. Care to eliminate any of these?
Yeah, I mean,
We
you could
don't.
say that.
Go ahead.
Well, no, that's only true for Newtonian. I mean, couldn't you say that since the velocity is just function of x2? No, I guess you have to go a little farther to start with.
Yeah. Well, there's one thing we could say, but we don't have to, because it'll come to us later if we want. We can't say anything about the taus, whether they're 0 or not, off the top of our heads, unless we're really, really experienced. But we can say something about how things vary in certain directions. So, for instance, x3. Yeah, x3 is playing the same symmetry role as we saw in the last problem. Nothing's going to be changing in the x3 direction. This is going to be a flow that is independent of width. So we could actually sit here and take these 3 derivatives with respect, no matter what the stresses are, they're not going to be a function of x3 in this flow, by the way we've modeled this flow as a unidirectional flow. So we could do that now, or later we could look at what tau is and see whether those are 0 or not. But either way, it's going to be we're going to lose these terms. Nothing varies. But if that's not comfortable, just wait and see what happens next. Okay, so we're either doing that or we're not. We'll come back. What would be the next step to evaluating del dot tau?
Constitutive equation?
Yes, we need the constitutive equation. So the constitutive equation is the power law, generalized Newtonian fluid, and that is tau equals m gamma dot to the n minus 1 times gamma dot the tensor with a minus sign out front. So here we're in the same boat as we were with pressure-driven flow in a tube. We need to evaluate gamma dot, then we need to take its magnitude and plug it in. So gamma dot is del V plus del V transpose. And we know a lot about V, right? What's V equal to for this flow?
Just V1 of x2.
Right.
0, 0.
V1 of x2, 0, 0. So when we write the del V out, again, we can use Einstein notation. And we end up with dv dx in every location. No plus signs in between. This is a tensor, not a vector. Andy, do you know how, Andy Cole, do you know how to fill these in? Where do they go? What are the subscripts on the x's?
They'd be 1 all the way across.
Right, 1 all the way across, then
2 all the way across.
2 all the way across, 3 all the way across. And then on the v's?
Just, yeah, your columns.
1 down the column, right. 2 down the columns, 3 down the column. Okay, so here we have a lot of stuff to simplify, right? We know that V2 and V3 are 0. What else do we know? Jason, what else can we simplify?
Since it was 0, because, let's see, it's in the x3, because it's so big.
Right, so this one goes out because of the width symmetry again. This is very wide flow. Any other term?
D1 and X1
Right.
go to 0, I think.
Right. This one is 0 because?
It's not steady state, is it? It's not steady. It's
No,
just-
that's not the reason. It's
yeah, that right there.
continuity equation, exactly.
Yeah,
So the continuity equation gets rid of that last
oh,
term.
okay.
So we're left over with just one term. And when we write del V plus del V transpose, we get a symmetric tensor again with dv1 dx1, x2 here and here. And everything else is 0. So it's getting into a pretty smooth rhythm, right? I mean, you can see you start with continuity, you go to the momentum balance. The momentum balance has things that we know some set things about. In the homework problem, when you do the Couette flow, the flow with double cylinders, it's not unidirectional flow. So you're not going to be able to say V dot del V is 0. So that is, maybe you'll remember that from doing that from the Newtonian case. But there is a centrifugal force term. So that doesn't go entirely to 0. And then we always leave the pressure to the end until we need to make a decision. And then we have to deal with, in this case, because of the non-Newtonian flow, we have to deal with the constitutive equation. So now we've got gamma dot. We need the magnitude of gamma dot. So we need gamma dot, double dot, gamma dot over 2, quantity square root, which is each element multiplied by its mirror image across the diagonal. So it's 0, dv1 dx2 squared, 0, plus dv1 dx2 squared, plus 0, plus 0, plus 0, plus 0, plus 0. So again, it's 2 dv1 dx2 squared over 2, quantity square root. And we get plus and minus dv1 dx2. Plus or minus? Plus. As we increase x2, the velocity is increasing. Now, if I had picked a different coordinate system, let's say I gave you this exact problem again, but I put the coordinate system up here going down, the story would be different, right? So you got to look every time. That's all. That's really the only tricky part. You have to look every time. If I were crazy and put the coordinate system in the middle, you know, you'd be a little confused probably, but you'd have to figure that out. You know, if I picked a completely crazy coordinate system, then you really would have some trouble. There are some problems. There's one very nice problem where you have to break the flow up into two different regimes. So for instance, let's say you have flow between parallel plates of two fluids, one with one viscosity and one with another. Okay? And maybe, so here, let's say you pick this coordinate system, and then you impose a pressure on this thing. So maybe the velocity field comes out something like this, and then maybe a little bit something like that, something crazy. Okay. Now, is dvx dy positive, negative, or 0? It's both. It's positive, right? As I increase y, the velocity is increasing, 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 decreasing, 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 decreasing. So I have to divide the flow up at this location and say, you know, in this regime, it's negative, so so the gamma dot value has to be the negative of the derivative, and in this regime, it's in the positive, and you have to split the problem into two. It's a little bit ugly, and there's an example in the book of that. Okay, but it's logical. It just gets a little messy, but the logic is exactly the same as what we're doing now. So this time, gamma dot is positive dv1 dx2. So now we assemble tau. Tau is equal to minus m gamma dot to the n minus 1 times gamma dot the tensor. And so that must be equal to 0 minus m gamma dot to the n minus 1 times gamma dot the tensor. In this case, there's just a component here. I'm filling in here, okay? I'm multiplying this as gamma dot the tensor, and the only place there'll be non-zero terms is where there's this dv1 dx2, that's that. And everything in front is the m gamma dot to the n minus 1. So the other components are 0, and then there's another one identical to this here, minus m gamma dot to the n minus 1 times dv1 dx2. We can now go back to our del dot tau, and we see that the 1, 1, 2, 2, 3, 3 are 0, and all the ones with a 3 in it are 0. So here, these all go out regardless. So we didn't really need to strain our brain on this, but it's helpful either way. All the ones with a 3 in them are 0, so these are 0. The 2, 2, and the 1, 1 are 0. And we end up with del dot tau, it's a vector, d tau 2, 1 dx2, d tau 1, 2 dx1, 0. And we know what those taus are. They're those m gamma dot to the n minus 1 terms that are on the other slide. So we can reassemble, we can go back and reassemble the momentum balance. There it is. It's 0 equals this term minus the del dot tau term that we just did plus this one. 0 equals minus dp dx1 minus dp dx2 minus dp dx3 minus del dot tau x1 del dot tau the 2 component, and del dot tau the x3 component was 0. And 0 minus rho g 0. Del dot tau, the 1 component, is d by dx2 of tau 2, 1. Tau 2, 1 is minus m dv1 dx2 to the n. If I look at this component, I can combine these two. They're both dv1 dx2. This is to the n minus 1. This is to the 1. So I add them and I get to the n. So is this term 0 or non-zero? Non-zero. Why, Andy? Right. V1 is a function of x2, so this is the term we definitely are keeping. Del dot tau 2 component is d by dx2 of tau 1, 2. D by dx1 of tau 1, 2. D by dx1 of minus m dv1 dx2 to the n. How about this one? Why? Right, not a function of x1. So this is the velocity, which is a function of x2, and when you take its derivative, you'll get some function of x2. But this is only a function of x2, not a function of x1, so the whole thing goes to 0. So even this is 0. So the 3 component is easy. Pressure doesn't vary in the 3 direction. The 2 component is easy. Pressure varies in the 2 direction due to gravity, so hydrostatic head. Okay? So we get dp dx2 equals minus rho g. And the 1 component, which is the one that really tells us about the flow, says dp dx1 minus d by dx2 of minus m dv1 dx2 to the n equals 0. Is there a pressure gradient in the x1 direction? No. This flow has no imposed pressure gradient. And so there's really nothing interesting to make the pressure vary in the 1 direction. So in fact, it's 0. So it looks like everything goes to 0, but it's okay because this simple derivative we can solve for the velocity field. And it is, in fact, a very simple velocity field. So we get these minus signs cancel each other. It's inside the derivative, but it can still come out. D by dx2 of m dv1 dx2 to the n equals 0. We can integrate that. That's the derivative of something equals 0, which means the something must be equal to a constant. Okay, so when we integrate this once, we get m dv1 dx2 to the n equals a constant. Divide through by m. We get dv1 dx2 to the n equals c1 over m. Take the nth root. This constant on the right-hand side is getting complicated, but it's still an arbitrary constant. So we could just rename it if we liked, since we still don't know what it is. But take your, make your choice. You can do that or not. Take that nth root, you get dv1 dx2 equals this constant, c1 over m to the 1 over n. Derivative equals a constant is a simple integral. v1 is equal to that constant times the variable plus another constant. So we get a linear velocity profile. Don't be fooled by this power or anything. This is all just a constant times the 1 variable there. And that's what we showed here all along as the answer, that the velocity profile was linear. If we want the stress, we have to evaluate the boundary condition. Those are simple. Boundary condition of no slip at the wall. At the top wall, it tells us the velocity is equal to v. At the bottom wall, it's equal to 0. And if we want the velocity, the stress, we have to go back to here, and we can get the stress at any point from the stress tensor. So there's definitely a pattern to these problems, and I think you've seen it. And I hope you'll have no trouble with the homework as a result of that. Now, normally I would go to my slides, but I unfortunately left my slides in the car, and the car is at the shop. So we'll see how well these show up on the image camera here. I apologize for that. So that's an example of how to use the generalized Newtonian fluid. Oh, these aren't even what I want to say. So,
So any fluid under drag flow will have a linear profile?
any fluid under drag flow will have a linear velocity profile at low rates. We assumed that if we put a sample between two plates and moved the top one, that the flow would only be in the one direction. So there are some materials that when you do this, they'll curl up. They're so elastic, you pull them this way, they mostly move in that direction, but the edges curl up. And so our assumption that the variation in the x3 direction is 0 is wrong. And our assumption, if the flow recirculates, our assumption that the flow was only in the one direction is wrong. Okay, so we made a lot of assumptions in getting this solution. So provided that the flow is carried out in such a way that the flow is only in the one direction and it's sufficiently wide that there is no reasonable contribution from the variations in the x3 direction, it's correct. There's a rheometer that was built by Professor John Deely in McGill University. It's called the parallel plate rheometer. Works in a vertical mode. Two gigantic, you take a big piece, you have a big plate here, and you slap your polymer on this plate, and then you slap another plate on it, and then it moves it. Okay? But it's interesting, when you actually carry out this exact flow very carefully on highly elastic materials, they sometimes do all this really weird instabilities on the edges. So the assumptions of this flow are in fact violated in some cases. So that's always the case when we make simplifying assumptions to solve problems. So I've only showed you examples of generalized Newtonian power law models for solving. We could do others, but I don't think it's that useful to us. The differences in the solution methods, if we use something other than the power law model, I think you can see where they happen. All of this is the same. It's only when we start to talk about the constitutive equation that it comes out different. So you may or may not, depending on, well, for another generalized Newtonian fluid, you'll also need gamma dot. For some of the constitutive equations, you need the magnitude of the stress tensor rather than the magnitude of gamma dot. But it's at the point where we try to evaluate the del dot taus that things will be different. You have to just follow the rules of whatever constitutive equation you're using. So this is really all I wanted to say about the power law models. The generalized Newtonian fluids. They have advantages and disadvantages. The advantages is that they're pretty good in pressure drop flow rate calculations. So that means that if you're doing a mold filling simulation and all you care about is how much pressure is going to be produced in that mold, you can use a power law generalized Newtonian fluid or a Karo-Yasuda generalized Newtonian fluid. One way they are at a distinct disadvantage is that they never predict shear normal stress effects. And we we've seen that, we can see that very clearly from the form of the equation. Tau is equal to some function times gamma dot. In shear flow, gamma dot is always going to be gamma dot 0, 0, gamma dot naught. Now I'm talking back in standard flows, where we always have the velocity of the standard flow at steady shear is gamma dot x2, 0, 0. So it will always look like this. It will never predict anything but 0 for shear normal stresses. So any problem that you're trying to simulate that has some component where that's important, it's not going to work. The other big disadvantage of the generalized Newtonian fluid is no time-dependent effects. And we can also tell that directly from the constitutive equation. This constitutive equation, I usually write it like this, tau equals eta gamma dot. But it's actually short for tau at the current time is proportional to gamma dot at the current time. Tau equals minus eta. Tau at the current time is equal to the shear rate at the current time. For materials that have memory effects, the stress at the current time can depend on what the shear rate, what the deformation was 2 seconds ago, 5 seconds ago, 8 seconds ago. Okay? So if you have silly putty and you stretch it, what you did a second ago and then let go, what you did a second ago depends what the material does now because it has memory. So anything that you want to model that has memory effects, we can't use these models. So I'll summarize that again next time. And then we'll move on to studying models where we'll try to fix this first, where the time dependence, we can use our heads a little bit and put together some simple models that tell us how the stress at the current time might depend on the deformation a few seconds ago. And we'll pull together some very simple models and we'll get to linear viscoelastic theory. It'll take us quite a few more lectures before we'll get anything that will predict shear normal stresses, but we will finally get there eventually. But first we'll try for the time-dependent effects. Okay? And that's it then, and the homework is due on Wednesday.